Okay, so firstly, let's talk about supervised learning. And supervised learning really is like having a teacher there or having a trainer there who's guiding you step by step, telling you that was right, that was wrong, or this is a flower, this is a plant. It's a sort of hand-holding way of teaching the computer what to do. So one of the most famous examples of supervised learning is training a computer to recognize a cat, right? So we would say to the computer, this is a cat. This is a cat, this is a cat, this is a cat, and this is a cat. And of course, as humans, it's very easy for us to look at any image and identify, whether if it's a cat or a dog or any other sort of animal. But essentially, we kind of went through this training process when we were young as well, right? When we were babies and we looked at this strange, fluffy animal, maybe one of our parents said, that is a cat. Or maybe your teacher said, that is a dog. And over time, we learnt pattern recognition. We understood how to classify different animals based on repeated exposure. And this is exactly what we do for machine vision. So we feed the computer loads and loads of cat images. And if there's one thing that the internet is not short on, it's cat images. And every single time we show it this cat image, the cat image also has a label saying this is a cat. So every single time the computer sees this particular blend of pixels, it'll be taught that that is a cat. So this is why it's supervised. The training data is always labeled. So what we're hoping for is after this repeated exposure, where the machine learns that this is the rough outline of what a cat looks like, then the next time when we ask the computer and feed it a piece of data that's unlabeled saying, what is this? The machine learning model should be able to identify that it has a lot of features that are very similar to the previous images of cat, and it should spit out the answer, this is a cat, even though it looks like a burrito. So when you're training that machine learning model, you're essentially presenting it with loads of images. And each image comes with a label. So the data is clearly labeled and gets fed into the machine learning model. So this is a cat, this is a dog, and this is a cow. Now, you're going to do this for lots of different types of cats, dogs, and cows so that you cover all the different breeds and all the different sizes or lighting conditions, etc. And the machine learns through this experience and begins to classify these images into their respective groups. So in this case, the model is the thing that does the learning, and the data that you feed it is called the training data. Now, once you've completed your training, at a later stage, you should be able to present an image of a dog that the model has never ever seen before. So this is not a part of the training data. And you ask the model, what is this based on all of your training? Can you classify what this image is? And it should use what it's learnt based on the training data and be able to spit out an answer and say, this is a dog. So the new image that the model has never seen is called the testing data, and the result that it spits back out is the output. Now, the output can be in various forms. It could be a word, or it could be a move on a chessboard. It really depends on how you trained up the model and what you want it to do. So this is one of the most fundamental types of supervised learning, and it's known as classification. So if you imagine you're trying to teach a computer to differentiate between apples and pears. Now, to us as humans, this seems like a really simple task. But if you imagined trying to turn this task into a programming exercise where you had to tell the computer what features it had to look for in order to tell the difference between an apple and a pear, it's actually a really, really complex problem. Because you could say maybe, oh, computer, if you blur everything up and you look at all the pixels in each image, the apple pictures tend to have more red colors than the pear pictures. So from our experience, we know that pears tend to be more green and apples tend to be more red. But if you decide to program the computer in this way, what happens when you have a green apple? Then the computer is probably going to think that's a pear, right? Now, also, what if you have some sort of fruit that it's never ever seen before? Even though you can write a lot of code and specify all of the unique features of apples when it's compared to a pear. So say if you said apples tend to be more round than pears, apples tend to be a little bit redder than pears, and then you try and present the computer with something it's never ever seen before that is an anomaly that doesn't belong in the apple or the pear camp, then it's going to try and use those rules that you defined and try and classify it, and it'll probably classify this as an apple. And through a lot of research, it's been demonstrated that even though we're really, really good at pattern recognition as humans, we can't always pinpoint exactly what it is that makes a certain thing that. I mean, try and think of what makes an apple unique amongst all the other fruits, or indeed any other item in the world. It's pretty difficult and time-consuming to come up with a program with a list of rules that classifies an apple and makes the computer differentiate it from a peach, for example. But in the case of machine learning, you can feed that machine learning model a whole bunch of images of cats, of dogs, of pears, of apples, of anything that you can imagine. And as long as all of those pieces of data are labeled and you give the model enough instances of each and every category, then it should be able to spit out what each of the items were and be able to classify them based on the features that it's identified. And the nice thing about a lot of these machine learning models is that they're reusable. So you could probably create a generic classifier that looks at handwritten numbers and is able to figure out what those numbers are. So turning it from an image to an integer, for example. But you can use that same generic classifier, and instead of training it on images of handwritten numbers, you could feed it emails that are labeled as spam or not spam, and it could classify new emails based on those criteria. So once you've created a good model or a good generic classifier, if you change the training data, you can get it to do different things without having to recode the entire model. And this is one of the advantages of machine learning. Now let's look at how a machine might do this. So say if we have a graph where we have a threshold for emails that should go into the inbox and a threshold for emails that should probably go into the spam folder. When you have a spam filter or an artificially intelligent program that is able to differentiate emails that come in, whether if they should head to the inbox or whether if they should head to the spam box, then it's kind of binary. You can't really have a halfway house, like maybe a decontamination zone or a sort of spam or maybe spam folder, right? So let's say that the decision is only binary. When this machine learning model gets fed new testing data in the form of an email, it should be able to scan through the content and decide whether if it should be sent to the inbox or whether if it should be sent to the spam box. So it's a 1 or 0. Now, let's say that we train this model on a whole bunch of emails which are labeled as spam or not spam. Now, let's say that one of the factors that affect whether if an email is likely to be spam is the number of links that are contained in the actual email. And this is a real thing, by the way. If you try and go onto Gmail and you send somebody an email that has 100 links, you can see which folder it lands in. It's usually not going to be an inbox because it just looks so spammy. So if we plot all of our training data onto this graph, so emails which are labeled spam or not spam, based on the number of links that the email contains, then it might look something like this. Now, the machine learning model's job is to try and draw a line that goes through this data and figures out a threshold for the number of links. So if, say, the number of links was less than 5, then it probably is more likely to go into the inbox. And if it's greater than 5, it's probably more likely to be spam, so it should go into the spam box. And this particular rule can be given a weight amongst many, many other features. For example, the number of images that are contained in the email, or the number of words like buy or sale. So it evaluates a whole bunch of these features within the email, and it has different weightings towards each of these features. And using all of that, it's able to decide whether if an email should be going to spam or going into the inbox. and it learns continuously over time. So every single time you mark an email as spam, then you're teaching that machine learning algorithm something new, whether if it's confirming its existing model or giving it new features or giving it new data to work on to be able to predict this with increasing accuracy. Now, the thing to remember is that in supervised learning, we've already spoken about classification problems. And classification problems tend to be applied when you have discrete data that fit into specific camps. So for example, your grades, right? You might get an A plus, you might get an A B plus, etc. You won't get like, a B plus 0.5 or a B plus 0.599. Instead, that would be called continuous data. So for example, your height, right? Your height could be anywhere along a ruler, and depending on how accurately you decide to measure your height, it could go down to 10 decimal places if you were really that interested in your precise height. So the reason why we differentiate between discrete and continuous data is that when you're working with continuous data with machine learning, you're more likely to be using a process called regression to do your machine learning. So a good example of a regression model is, for example, developer salaries, right? So according to Indeed.com, the average salary of a developer, it doesn't say what kind of developer, is about $100,000 per year. And this is based on data from about 1,500 employees over the past 12 months. It also shows you this box, depending on the level of experience of the developer, they might get paid less or more. So this is something that we would probably tend to agree with, right? If you've worked for a longer number of years at a particular job, you're probably going to get paid more. Now, say if you had a friend who came to you and said, I've worked as a developer for 12 years. How much do you think that I'm likely to get paid if I apply for a job right now? Now, you can give him a rough estimate, putting him into one of these camps, right? Maybe 12 years puts you into, your average developer, or maybe if he's worked for 20 years, then that puts him into the senior developer camp. But you can't really say for sure exactly what number it should be based on his exact input, i.e. 12 years. So this is where a regression learning model comes in handy. Let's say that you plot a graph of developer salaries. And on the y-axis, you've got the salary, and on the x-axis, you've got the years of experience. So you're looking at the years of experience as an independent variable to the salary of a developer. So this is what that graph looks like if you give it a whole bunch of training data, i.e. clearly labeled data. So each data point has a salary amount and the years of experience of that developer who is earning that salary. Now, in most cases, even if you have 0 years of experience, you're not going to start out with a salary of 0 because even interns get paid, right? So that first data point is maybe the entry-level standard salary. But as you can see, using your human eye, as the years of experience increase, you generally see an increase in the amount of salary they earn. Now, if I told you to try and draw a line through all the data that best fits this particular data set, you might be able to do it quite easily. And similarly, this is what we want our regression model to do. We want it to draw a line through the data that best fits this particular data set. And now that we have our regression model, we're able to go onto the x-axis and look at where 12 years of experience will hit the line at. And then if we extend it to the y-axis, we can see, based on our training data, what amount of salary our friend who has 12 years of developer experience should be earning. So this is a very, very simple representation of a regression model. Now, of course, there's other types of supervised learning models, but the most common ones that you will see and the most common ones that are used commercially are regression and classification, both of which CoreML is able to do. Now, in the next lesson, we're going to talk about another type of machine learning, which is unsupervised learning. So I'll see you there.